Okay, so we have a statistical mechanics and computational physics practice exam, final exam, graduate level. So let's begin. Number one, and I'll try to go through this rather quickly. You have this as a reference. Number one, a system contains n distinguishable absorption sites on a catalytic surface. Each site may be empty or occupied by a molecule of energy, negative epsilon. Exactly n sites are occupied. Part A, using Boltzmann's entropy hypothesis, S equals K sub B, Ln omega, derive the configurational entropy of the system. Okay, so Boltzmann entropy and Helmholtz free energy problem. So A, entropy, the number of ways to choose n occupied sites, is the following. Omega equals this n choose n formula. And using Boltzmann's formula, S equals K sub B Ln omega. So S equals K sub B Ln of n factorial over lowercase n factorial times the quantity capital N minus lowercase n factorial. Using Stirling's approximation, Ln of capital N factorial is n ln n minus n. So we get S is approximately K sub B times this whole quantity here, this n ln n minus lowercase n ln lowercase n minus capital N minus lowercase n ln of capital N minus lowercase n. We're going to let theta equal lowercase n over n. And then S equals negative n times K sub B times the quantity theta ln theta plus quantity 1 minus theta ln times 1 minus theta. Okay, we're going to go to the second page of this, but I'm just going to read these three. So just for letter B, using Stirling's approximation, derive the Helmholtz free energy, F of t, lowercase n capital N. Part C, determine the equilibrium fractional coverage. Theta equals lowercase n over capital N by minimizing the free energy at fixed t. And part D, discuss the behavior of theta of t in limits t going to 0 and t approaching infinity. I should say t approaching 0 and t approaching infinity. Okay, so that being said, for letter B, the Helmholtz free energy, here's what we can do. Helmholtz free energy, U equals negative n times epsilon equals negative capital N times theta times epsilon. The Helmholtz free energy is F equals U t minus Ts. So we're going to get F equals negative n theta epsilon plus n K sub B capital T times the quantity theta natural log theta plus 1 minus theta log 1 minus, or ln, however you want to say it, ln times the quantity 1 the quantity 1 minus theta. Okay, moving along to letter C, equilibrium coverage. Okay, so what we want to do here is minimize F with respect to theta. So we're going to take that partial derivative here, df d theta. We're going to get negative n epsilon plus n K sub B t times this quantity, ln theta minus ln of 1 minus theta. Then we're going to solve here. This is going to set it equal to 0 rather. First, negative epsilon plus K sub B t ln of theta over 1 minus theta, that equals 0. Solving for this, we could exponentiate both sides. And we're going to wind up with, after we do the algebra, theta equals 1 over 1 plus e to the negative epsilon over K sub bt. Okay, some of the intermediary steps I leave out, but that's just for the sake of brevity. Letter D, okay, we want the limits, as were shown on the previous page. So as t approaches 0, e to the negative epsilon over K sub bt approaches 0, so that would mean theta approaches 1. And at very low temperature, all favorable sites are occupied. As t approaches infinity, e to the negative epsilon over K sub bt, that approaches 1, so theta approaches 1/2. And at high temperature, entropy dominates and occupied, unoccupied states become equally likely. Okay, so that's for that one. That's number 1. Let's move along to number 2. Okay, so again, I'm going to go through this rather relatively quick pace. Okay, let's see. Okay, so here we want to consider, it says consider a mean field model of a pneumatic liquid crystal with orientational order parameter Q. Okay, we get the Gibbs free energy density is that G of Q comma T equals G naught plus A over 2 times the quantity T minus T sub C times Q squared minus B over 3 Q cubed plus C over 4 Q to the 4th. We're going to assume A, B, and C are greater than 0. So part A, we want to determine the equilibrium condition for Q. Okay, so Gibbs free energy in liquid crystal ordering. Here's what we do here. Equilibrium condition requires that partial dg with respect to Q equal to 0. So this partial derivative dg dq, that partial equals A times the quantity T minus T sub C times Q minus B Q squared plus C Q cubed. Factoring out a Q, we get Q times the quantity A times the quantity T minus T sub C minus BQ plus C Q squared equals 0. So we're going to wind up with Q equals 0 or CQ squared minus BQ plus A times the quantity T minus T sub C equals 0. And the non-zero solutions are up there. Q equals B plus or minus square root of B squared minus 4AC times the quantity T minus T sub C over 2C. So that's letter A. Letter B, find the critical points and determine which are stable. So stability is going to require that second derivative, that partial second derivative with G respect to Q is going to have to be greater than 0. So we take that second partial derivative there, G respect to Q. We wind up with A times the quantity T minus T sub C minus 2 lowercase bq plus 3C Q squared. So now at Q equals 0, that second partial, G with respect to Q, is A times the quantity T minus T sub C. So capital Q, that equals 0, is stable for T is greater than T sub C, and unstable for T is less than T sub C. The non-zero state is stable when the quartic term produces a local minimum. Okay, so that's letter B. Let's move along to letter C. So let's read letter C, D, and E first. So we have them show that the transition is first order. That's for C. Describe the free energy landscape above and below T sub C. That's for D, just so we have it, so we know for the next page. And E, explain briefly why liquid crystal displays rely on orientational order. Okay, so moving along here to number 2, letter C. Okay, so first order transition here. Okay, because the free energy contains a cubic term, negative B over 3 Q cubed, the free energy is asymmetric in Q. A cubic term generally causes the ordered state to appear discontinuously. At coexistence, the ordered and disordered phases have equal free energy. G of Q star comma T star equals G of 0 comma T star. Since G of 0T equals G naught, requires A over 2 times the quantity T star minus T sub C times Q star squared minus B over 3 Q star cubed plus C over 4 Q star 4. That equals 0. Okay, now also equilibrium requires A times the quantity T star minus T sub C minus B Q star plus C Q star squared equals 0. Using these together gives Q star equals 2B over 3C and T star equals T sub C plus 2B squared over 9AC. Since Q jumps from 0 to 2B over 3C, the transition is first order. Okay. Part D. Part D, they wanted us to describe the free energy landscape above and below T sub C. So, for high T, the minimum is at Q equals 0. Near the transition, a second minimum appears at non-zero Q. Below the transition, the non-zero Q minimum becomes lower than the Q equals 0 state. All right, and letter E, explain briefly why liquid crystal displays rely on orientational order. Okay, liquid crystal displays work because molecular orientation changes the optical response. The order parameter Q describes how aligned the molecules are. Electric fields can reorient the molecules, changing polarization transmission and therefore brightness. Okay, so that's number 2. Let's move along to number 3. Okay, so for number 3, we have a polymer consists of n freely jointed segments of fixed length A. Part A, using random walk statistics, derive the probability distribution for the end-to-end vector R. So polymer chain statistics and rubber elasticity problem. So for part A here, end-to-end distribution, a freely jointed chain has n segments of length A. For large n, the end-to-end vector follows a Gaussian distribution. So P of R equals that 3 over 2 pi n a squared to the 3 halves exponential negative 3 r squared over 2 n a squared. Okay, so that's for letter A. Letter B, compute the entropy S of R associated with fixed extension R. Okay, so entropy here, since S equals K sub B natural log of omega, and the probability is proportional to the number of configurations, S of R equals S naught plus K sub B ln P of R. If we ignore the constants, S of R equals S naught minus 3, K sub B R squared over 2 n a squared. Okay, so that's letter B. Letter C, derive the entropic restoring force for small extensions. Helmholtz free energy is F equals U minus TS. For ideal rubber elasticity, U is approximately independent of R. So F of R equals F naught plus 3 K sub B T R squared over 2 and A squared. Okay. So from here, we get the force is F equals dF dr. And therefore F equals 3 K sub B T over NA squared times R. And the restoring force is the opposite, the extension direction. Okay, so the restoring force is the opposite, the extension direction. Pardon me for going out of focus. Part D, explain why rubber elasticity is predominantly entropic rather than energetic. Okay, so right here, stretching a polymer reduces the number of possible chain conformations. The restoring force comes mostly from the tendency to maximize entropy, not from stretching chemical bonds. Okay, that's letter D. Letter E, we have estimate the temperature dependence of the elastic modulus. So right here for letter E, since F is proportional to T, the elastic modulus also scales approximately as G is proportional to T. And rubber becomes entropically stiffer at high temperature. Okay, so that's number 3. Moving along to number 4. Oops, sorry. Okay, number 4. All right, so number 4, consider a three-dimensional crystalline solid described by Debye theory. Part A, derive the density of vibrational states G of omega. Okay, so Debye theory of crystalline solids. So part A, in 3D, the number of vibrational modes with wave vector magnitude less than k is proportional to the volume of a sphere in k space. N of k is proportional to k cubed. For acoustic phonons, omega equals vk. Thus, G of omega equals dn d omega, proportional to omega squared. Okay, and if we normalize so that there are 3n modes, if we integrate here from 0 to w sub d, 0 to omega sub d, here we get G of omega dw equals 3n, G of omega equals a omega squared. Here a omega sub d cubed over 3 equals 3n. And so A equals 9n over omega sub d cubed. Therefore, g of omega equals 9n over omega sub d cubed times omega squared. Pardon me, sometimes I pronounce omega as a W if I read too fast. It happens. Part B, obtain the Debye heat capacity expression C sub V of T. So the internal energy is here, this U equals this integral from 0 to omega sub D of this G of omega times that H bar omega over e to the H bar omega divided by K sub BT minus 1 d omega. Okay, using X equals H bar omega over K sub BT, the Debye heat capacity becomes this C sub V equals 9n K sub B T over theta sub D, and then we're going from 0 to theta sub D over T of this integral here, x to the fourth, e to the x over the quantity e to the x minus 1 squared dx. Okay, hopefully I didn't mispronounce too many things here, but the math is okay. Again, I'm going pretty fast, speaking fast, so I'm prone to make some mistakes. My apologies with the verbiage. Letter C, show explicitly, sorry about that, that C sub V is proportional to T cubed for T is much less than theta sub D. Okay, so right here, low temperature limit for T is much less than theta sub D. The upper limit becomes approximately infinity. So we're going to integrate from 0 to infinity, that integral from before here, that component x to the fourth e to the x over quantity e to the x minus 1 squared dx. That's going to equal, when we do the computation, 4 pi to the fourth over 15. Therefore, C sub V equals 9n K sub B times quantity T over theta sub D cubed times 4 pi to the fourth over 15. So C sub V equals 12 pi to the fourth over 5 n K sub B times the quantity T over theta sub D cubed. So we could say C sub V is proportional to T cubed. Part D, explain physically why the classical Dulong-Petit law fails at low temperatures. And pardon me if I'm not pronouncing the name properly. I've heard it pronounced different ways. Of course, you're supposed to pronounce it the French way. I'm not good at languages. My apologies. Letter E, letter D, what we could say is classically each vibrational mode contributes K sub B to heat capacity at low temperature. Many high frequency phonon modes are not thermally populated because their energy spacing H bar omega is too large compared with K sub B T. Okay, and part E, material has a Debye temperature theta sub D equals 420 K. Estimate the temperature range where quantum effects dominate. Quantum effects dominate when T is much less than theta sub D. With theta sub D equal to 420 K, a reasonable estimate is this for this T. Okay, about 42 K. Okay, if it goes to a tenth, if we're saying that it's about approximately less than 1/10 of theta sub D, that would be about 42K. Sorry. So that's, I'm sorry for any mispronunciations. That's number 4. Let's move along to number 5. Okay. Alrighty. Okay, so just, sorry about that. Okay, so using the DS model, analyze electron transport in a metal. So derive the electrical conductivity, sigma equals Ne squared tau over M. Okay, so electrical conductivity in crystalline materials. So our conductivity here, an electron under electric field E, field's force F equals negative lowercase e times E, the electric field. The acceleration is m dv dt equals negative e times capital E. Between collisions, the average drift velocity is v sub d equals negative e tau over m times the electric field. The current density is J equals negative NE V sub D. Substitute J equals NE squared tau over M times E. So sigma equals NE squared tau over M. Okay. Part B, show how the Fermi-Dirac distribution modifies the classical picture. The Sommerfeld correction. In a metal, electrons obey Fermi-Dirac statistics. F of E equals 1 over E to the quantity E minus mu over K sub BT minus 1. Okay, only electrons near the Fermi surface can respond effectively to fields because states deep below the Fermi energy are already occupied. Thus, the true result remains similar in form, but V, scattering and carrier response are determined by Fermi surface physics. At low temperature, phonon scattering becomes weak. Remaining resistivity from defects, impurities, dislocations, and boundaries. We have this rho of T approaching 0 equals rho naught. Part D, discuss the electron phonon scattering and derive the approximate temperature dependence of resistivity at high temperatures. So part D, at high temperatures, that T is approximately, that's larger, should be around larger or equal to about, it should be around, should be bigger usually than the theta sub D. And phonon population is roughly proportional to T. So more phonons mean more scattering, so that T to the negative 1 or T inverse is proportional to T. And since rho is 1 over sigma, that's proportional to 1 over T, and we get rho is proportional to T. Pardon me if I mispronounce anything. Okay, and E, why do some crystalline solids behave as insulators despite containing many electrons? So in band theory, a filled valence band and empty conduction band separated by a large band gap prevents low energy electronic conduction. Electrons cannot easily move because available conducting states are energetically inaccessible. Okay. Right here, just a note, at low temperatures, metals may have Bloch-Grüneisen behavior, which means they're not going to behave simply like the linear T. Okay, so that's number 5. Sorry if I spoke too fast, mispronounced some things. It tends to happen. Let's move on to number 6. Okay, number 6. Okay, whoops. So, an oxygen ion solid electrolyte obeys Arrhenius transport behavior and derive for letter A the logarithmic linearization used experimentally to determine E sub A, and we're given here for this sigma of T equals this sigma naught times E to the negative E sub A over K sub BT. So, fuel cell solid electrolytes problem, linearization. So we take what we're given for that sigma of T. We're going to take the logarithms here, ln sigma, that equals ln sigma naught minus E sub A over E sub B times 1 over T. And so a plot of ln sigma versus 1 over T, that's going to have a slope of negative E sub A over K sub B. Okay. Letter B, describe the microscopic origin of ionic conductivity in oxygen vacancy conductors. So in letter B here, in oxygen vacancy conductors, oxygen ions move by hopping into neighboring vacancies. Conductivity requires both mobile ions and deflects that provide, and defects that provide available sites. Okay. Letter C, a material has E sub A equals 0.85 eV. Estimate the conductivity ratio between 600K and 900K. So the conductivity ratio is going to be sigma of 900 over sigma of 600. So we're going to get this sigma naught e to the negative EA over KB 900 over sigma naught e to the negative EA over KB 600. That's going to yield E to the E sub A over KB of the quantity 1 over 600 minus 1 over 900. Use E sub A as 0.85 eV, so K sub B is 8.617 times 10 to the negative 5 eV per K. So E sub A over K sub B, that's 0.85 over 8.617 times 10 to the negative 5th, which approximately is 9,864. So we're going to have 1 over 600 minus 1 over 900. That's going to equal the 300 over 540,000, which is 5.56 times 10 to the negative 4th. So we're going to take that 5.56 times 10 to the negative 4th, multiply it by the 9864, and we get 5.48. So this ratio, sigma of 900, sigma of 600, that's e to the 5.48, which is about 240. Part D, explain the thermodynamic trade-off between ionic conductivity and structural stability. Okay, so for letter D, more defects increase ionic conductivity, but too many defects can destabilize the crystal structure, produce mechanical weakness, or cause chemical degradation. And part E, why are high-temperature solid oxide fuel cells often more efficient than low-temperature electrochemical systems? Okay, so here for E, high-temperature fuel cells often have faster electrode kinetics, lower activation losses, and can use waste heat more effectively. High temperature also improves ionic conductivity in solid electrolytes. Okay, so that's number 6, and let's move along to number 7. Okay, so number 7 here, consider an amphiphilic molecules in solution forming spherical micelles. Write an expression for the total free energy associated with the micelle formation. So surfactants and molecular self-assembly. So free energy of micelle formation for letter A. For a micelle containing M, surfactants. Sorry, I always have trouble pronouncing that word. My apologies. And I think I even, if I'm not mistaken, misspelled it. Sorry about that. Okay, so here's what we're going to get. We're going to get delta G sub M equals delta G core plus delta G interface plus delta G subhead, and then minus T delta S sub mix. Okay. Part B, identify the entropic and enthalpic contributions. For part B, favorable contributions, delta G subhydrophobic is less than 0. Unfavorable contributions include loss of translational entropy and electrostatic head group repulsion. Negative T delta S sub mix is greater than 0, and delta G subhead is greater than 0. Micelles form when the net free energy per surfactant is lower in an aggregate than in solution. Sorry about that. Letter C, derive, whoopsie-daisy. Letter C, derive the condition for the critical micelle concentration, CMC. So CMC condition at equilibrium, the chemical potential of a monomer equals the chemical potential per molecule in a micelle. Mu sub 1 equals mu sub M over M. For ideal dilute monomers, mu sub 1 equals that this entire term here. And then we get this U sub 1 equals C sub CMC equals this. So we get our C sub CMC proportional to the exponential of U sub M over M. Going from here to here, the 1 to 0, the first order, and over K sub B T. Sorry about that. Sorry, losing my voice a bit. So I kind of skipped over that. I'm just going to pause after this video and do a second part. Sorry about that. Part D, explain why micellization becomes favorable above the CMC. Okay, so for D, below the CMC, added surfactant mostly increases monomer concentration. Above the CMC, monomer concentration remains nearly fixed. An additional surfactant enters micelles because aggregation lowers free energy. Part E, discuss how temperature influences self-assembly. So temperature influence, temperature affects hydrophobic interactions, head group hydration, chain packing, and entropy. Depending on the surfactant, increasing temperature may either promote or disrupt micellization. Okay, so I'm just going to pause here. That'll be part 1, and I'll do part 2 when I get my voice back. Thank you.